Good morning, everyone, and welcome to the Rust project track for the day, and more importantly, day 2 of Rust Week. So welcome to the second day. I'm Adam. I'm going to be hosting this stream today, so if you're in this room all day, you are going to be very sick of my voice by the end of the day. I'm a member of the Crates.io team and also help out with RustSec. So I've got a few house rules, logistics, housekeeping things to get through first. The most important is if you need to find an organizer or if you need to ask them anything, you are looking for these people in lovely yellow shirts as being modeled down there right now. They can help you with
two mutable references into it. But actually this doesn't work. If you try to use them, then you get an error. The reason you get that is that here what's happening implicitly, to access the contents of pyref, the compiler inserts a call to deref_mute. This is what it looks like. And you will notice that the second call of deref_mute takes ~mute pyref. So it needs full exclusive access to the whole pointer in order to derive the mutable reference. And what this does is that this invalidates the first one we took. So you can write these two things, but then A is no longer valid to use. However, if this here was box, because box has special compiler support, this actually works. And if this here was a mutable reference, that also works. So deref_mute sort of cannot express the thing we want to. And here again, we need a different way of thinking about these operations that could allow this very nice ergonomics. And this is our segue into the proposal we came up with that sort of rethinks these traits in a way that enables a lot of the ergonomics we want.
Exactly. And so if we start with looking at what we already have, which are beautiful deref and deref
Welcome back. Again, if you didn't feel like you had enough borrow traits, we are going to have reborrow traits now, so this is even more exciting. Our next speaker is Abo, TypeScript developer.
Field by field memcopy, copying your A from the source to an A in the target, and same thing B to B, regardless of which order they are in. And we can actually also, at the same time, drop out some fields from the source, because it's totally fine to drop some fields out. It's just less copying for us. We can't, of course, add any fields. That would be wrong. But still, this is like mostly kind of simple. You need to have some lifetime coming from the source, and sometime that then carries on to the target. Everything works out fine. Today, we again only require or only allow one lifetime and only 1 or 0 data fields. That gives us the code gen to be just copy. And it means that the implementation today, the trait today in Nightly is buggy and unsound because we, for instance, forgot to check for alignment between the two types. Oops. Yeah. So there are some problems. There will always be problems, especially in the current economic situation. And there are some unresolved questions. In general, do we want to only support reborrowing a single lifetime? Or should it be allowed to have multiple mutable references in a struct and then reborrow all of them at the same time? If we don't allow that, then should we actually have that one reborrowed lifetime in the trait itself? So we would have reborrow of reborrow of tick A. That would maybe make some things easier. And kind of regardless of what we do, we might need to create a new phantom type, phantom exclusive, which explains that, yes, this is the lifetime that is being reborrowed here. If you're only reborrowing exclusive references inside of your own custom struct, then you don't need this phantom exclusive. But if you have a 0-size type, for instance, then you do need that. Some bivariance problems as well. For co shared, we might want to go back into an associated type, and it's not sure if we really want to require the target to be copy. Conceptually, it must be, but it doesn't necessarily need to be in the trait. Anyway, I am out of time, and I'm mostly out of things to say as well. So now, if you have things to say, tell me. Otherwise, I'll be around, and there's a smorgasbord of links out there. Thank you.
Okay, we have about 30 seconds if somebody near the front has a burning question that they really want to ask. Going. Okay. Well, where am I going? Here we go.
If the object being reborrowed has mutable references in it and you're executing this under Miri, does it retag them right now?
Yes, it does. Yeah, I think so. It should.
And like transitively, like if it contains a type, it like traces through the type and
it should.
Cool.
Eventually.
Thank you once again. It is now lunchtime. Lunch is downstairs. If you have allergies and you put them on your form, you will find your lunch at the Rund bar, which is the second one
GitHub actually introduced their own Bors-like feature. Of course, now we know it as GitHub merge queues, and this even made Graydon like quite happy that finally they are trying to resolve this this issue. So we essentially like had to figure out in 2022 like what are we going to do. This Rust implementation was essentially abandoned. It wasn't maintained. It didn't do what we needed, so we didn't use it. The Bors NG implementation was interesting because it almost did what we needed, but it was an external project, and I wasn't confident that we could make changes to it required for a compiler. Also, it was written like in Elixir, and like we didn't want to, I guess, contribute to something that was written in Elixir. That was a good choice because just a few months later, it became deprecated, and the authors essentially said like, hey, just go use GitHub merge queues instead. So what about the merge queues? Well, luckily, another member of the Rust project, Eric Haas, wrote another big Markdown document where essentially he tried to use the merge queues for all our a bunch of our repos. And it turns out we could actually use GitHub merge queues for everything except for the main compiler repo. Why is that? Well, the compile repo is kind of special. It's quite big. It has a lot of traffic. We manage like 30, 45, 40 PRs per day, which is quite a lot. And the problem is that the CI is quite expensive and quite slow. Like it can run like 85 jobs. It can take like 3 hours to finish. When you multiply this, it gives you like millions of build minutes every month, which is super expensive. Now, luckily, we have an agreement with GitHub, so they kind of like pay for all of this. And also, Marco from the infrastructure team did a lot of great work last year to optimize the cost of like each merge that we do. But even if we don't take the cost into account, we need to take the duration into account. As I said, it takes 3 hours. And if we just merge the pull requests one by one, we could only merge like up to 8 PRs per day, which is really not enough. So we need to somehow batch them. Now, the GitHub merge queues actually do merge the PRs, but they do it in a very aggressive way when they essentially like stack these pull requests on top of one another and run the CI repeatedly, which doesn't give us a choice to select like which PRs will be merged together. What Homu and Bors does instead is that we have a web UI, and essentially we manually select which PRs will be tested together based on like intuition and vibes. And then Homu will create a pull request with all the PRs merged together, and then we run CI for them just once, which amortizes the cost of the CI. Now, the biggest rollup that I found in the history of Rust is this one with 45 pull requests, which is actually super impressive because if you think about it, every PR that you add to the rollup kind of increases the chance that the test will somehow fail. And also, I saw in the history that like 10 years ago, it used to be that we had like a Monday rollup, Tuesday rollup, Wednesday rollup. But these days, we have like 3, 4, 5 rollups per day. So the bandwidth is like much higher. Okay, so to sum up, the merge queues had some issues. They wasted CI compute. They weren't really configurable enough. They didn't have the rollups. So the only remaining thing that we could do, obviously, is to rewrite the whole thing from scratch in Rust. Right? So why do I rewrite? Well, I wanted us to own the code, to be able to like customize it to our needs without depending on other reviewers, external reviewers. I wanted to have better error recovery and race condition handling, have some actual tests, make it possible for Rust people to contribute to Bors again. And actually, the biggest thing was that I wanted us to trust it, that it will be working without us having to babysit it. Also, at the time, I asked one infrastructure team member, like, how difficult would it actually be to re-implement Rust? And he told me that it's essentially a weekend project. So yeah, I thought that this would be like much easier than it eventually was. Spoiler alert, it didn't take me a weekend, it took me over 3 years, but luckily we did get to the end. So in 2022, the Rust-Lang Bors implementation, which is like just the new Bors or just Bors, was created. It's essentially a pretty classic Rust async application with like Tokio, Exum, Octocrab, SQLX, and so on. By the way, fun fact, I noticed that, I don't know what is in the air, but it seems that around December, it's a very popular time to start new Bors implementation. So I don't know why, but it somehow seemed funny. So what was it like to implement Bors? Well, if you have an old project that you port to a new one, it's a good idea not to like throw away all the old knowledge and at least like try to reuse its tests, right, to inspire the new implementation. Well, that was my plan, but the problem was that there were like essentially no useful tests outside of like parsing comments from a string. So I had to do it the old-fashioned way. I like read the source code, I talked to people, and I tried to like figure out from first principles what should Bors be doing. And it turns out there's a lot. Like it has to authenticate with GitHub, handle webhooks, parse comments, permissions, all kinds of pull request features, implement rollups, check manageability of pull requests, and then maybe at the end of the day, actually merge some PRs. But that's like not even the main thing. So if this sounds complex, it kind of is, and I wanted to have a lot of confidence that it will be working, that I wouldn't have to like wake up every other day and see a Zulip thread that Boris is broken again. So the first thing to achieve that was, of course, to write it in Rust, because that kind of moves a lot of the runtime issues to compile time. But I wanted to go further. So for example, we use the pretty cool SQLX library and the compile time checking of SQL queries, which gives us like very quick feedback if we had some errors in our SQL. And I also try to use the type system to our advantage. So for example, there is a function for merging a PR into a branch, and this cannot ever be done like in parallel by multiple instances of Bors. So and it is handled by database lock. So I created this like fake type that essentially can only be created when the database lock is held. And to call the function, you kind of have to like prove that you are holding the database lock. Otherwise, you won't be able to like merge something on a GitHub branch. I quickly figured out that implementing Bors is like the first 95% is like doing a merge queue, and the remaining 95% is like dealing with GitHub. I don't know how many of you like wrote a non-trivial production application with the GitHub API, but it's not a very friendly environment. In fact, I would say that it is like an adversarial environment that is trying to fight you at every opportunity. So for example, what it likes to do is like not send you webhooks, which are the HTTP notifications that tell Bors that something has happened in the repo, or delivering them a little bit late, or delivering them like 12 hours late, which is very fun if you're trying to debug like why is the webhook not being delivered. Or it can outright like lie to you. So recently we had a case where Bors was repeatedly trying to merge a PR that was already merged. Why? Because the GitHub API was claiming that the PR is still open, which was nonsense. So the fix for that was actually like no longer trusting GitHub. So we actually have to like reconcile the GitHub API state and our own database state, and sometimes we have to like choose which one we will trust. So that's a lot of fun. Also, sometimes GitHub is like non-idempotent in the retries. For example, I post a comment, it gives me like 500 error, nothing happened. I tried again and returns 200, right? So I would expect like there is one comment created. Nope. It can sometimes like do the thing you asked it to do, even though it returns 500, and there is like no way to tell. So that sucks. This like missed webhooks actually has a very high cost, because when you prepare the merge commit, you run CI, everything finishes okay in 3 hours, but then you miss the webhook. Well, Bors will then wait 3 more hours for a timeout and then like start again. And this wastes a lot of time. So we actually go to great lengths to do this in a more robust way, where we actually listen for the webhooks, but we also periodically have some background jobs that are checking like what is happening on GitHub and try to reconcile those like 2 sources of truth together. So that's nice. That's a lot of like complexity. And I knew that I wanted to like have big like confidence in the tests. So first we created this Bors kindergarten repository, which is essentially a school where Bors goes to try to learn how to merge PRs. And this is a great staging environment, but it was not enough. I also wanted to have like very powerful integration tests. And I approached that from a couple of directions. So the first one is a database. Now, when you have a web application with a database, it's always very hard to test, because like, what the hell should I put here in the test? And somehow the first instinct tends to be like mock it with an interface or a trait, and then implement it with a hash map in the tests. Great, but your reward for this is that it will crash in production, because surprise, surprise, hash map is not Postgres, right? So this is not a great solution, and I had experience from other bots that this will not work. So instead, we use this SQLX test macro, which will essentially inject a fresh database into each test, run the migrations, run the test, and then drop it. So we need to run Postgres when we execute the test, which is a little bit annoying, but it gives me much more confidence that it will be actually working against a real database. This was not perfect. We also ran into some like production errors around migrations. For example, when we have a migration that added a new column that was not null, but didn't have a default value, so it failed. I tried to like mitigate this by adding a big warning into the documentation, do not ever do this again. However, that's not the best we could do. In Rust, I can actually include a production-grade SQL parser with 1 line of code, and then I can actually write a test that will like parse all my SQL migrations and check if they don't have like this bad property of adding this not null column with the default. So Rust was quite helpful here. I also wanted to test the GitHub integration. So GitHub sends webhooks to Boris, and Boris then communicates with the GitHub API via HTTP. How can I test this? Well, I could re-implement GitHub, but I probably cannot do that, even though like this would probably be a pretty good approximation these days. Or I could deploy GitHub locally, which is not possible as far as I'm aware. I could test on real repos, but that would maybe be the best way. But it's a lot of work, and it would be probably quite slow. So I settled on mocking the HTTP endpoints. So in the tests, I create these fake webhooks, I send them to Boris, and then I mock a subset of the GitHub API using the virmock crate. And the important thing is that there is not a single line of mocks inside Boris. It actually thinks that it is running in production, which is quite cool. This virmock library is pretty nice. It allows me to say, like, hey, when there is a request to this regular expression, I can run some Rust code. I can parse something from the request. And then based on the test state, I can like simulate, hey, now is GitHub the happy path. It is returning 500. Or it is like returning the actual data or 404 or whatever the hell I want, which is pretty nice. And finally, I wanted to also test like the async stuff, all the race conditions. Now, my experience with testing Boris, with testing async code without Boris was actually quite painful because a lot of async code looks kind of like this. And this is essentially like impossible to test, right? So especially in Boris, we have a lot of background jobs. And if you implement it naively like this, it is very hard to test. Like, I don't want to wait 30 seconds between something happens in the test. I don't want this thing to like run forever. I don't want it to do like the background job whenever it wants, because that can lead to flaky tests, which is always annoying. So in Boris, we kind of invert the control flow. We have these queues that explicitly tell the background jobs when they are supposed to start doing something. And this gives us a lot of control and also proper cleanup, because when the queue is dropped, the whole background process will kind of finish and handle all like errors and stuff like that. And then in the test, I can actually decide, like on a granular level, what will be the interleaving of the individual async operations to simulate various race conditions. Now, this is still not perfect because this only gives me the opportunity to start something, but not to finish it. So how to wait before something completes or finishes? Well, one approach is to like spam sleep calls inside the code, but that doesn't really scale. Another one is to synchronize through some external state, like a database or an HTTP call, which is the most common thing. But sometimes in the test, I need to wait for something internal happening inside Boris. And for this, I use something called coverage marks, which is an idea that I found through Matplotlib. And it's essentially a global variable where the code, like the normal code of Boris, can say like, hey, I went through this line of code, so I mark this variable. And then in the test, I can wait until the variable has been marked, and only then I can, for example, assert that something has happened. So this is also pretty nice for like combating flaky tests and these kind of annoying situations. This comprehensive test suite also allowed me to find really like weird bugs. So for example, here I was sending some HTTP request with somebody, and I was simulating in the test that it returns the 500 error code. And then Boris was supposed to retry it. So it did, but somehow it didn't send the body again. So there was like a super weird error. I was trying to like find the error everywhere using Wireshark and like mocking various dependencies and so on. Eventually, I tracked it down to a bug in the OctoCrab crate, which was implementing retries, and it said that like requests can be cloned, but at the same time, it was still like cloning the request. So what was the problem? Well, the request body was essentially an arc mutex. So it was cloning the arc, and after the body was sent, the mutex content was like consumed and it disappeared. So that was a pretty annoying bug. Luckily, I was able to fix this bug for everyone using OctoCrab. However, the most important thing is that without this test suite, I wouldn't ever find this bug. Like there is like literally no chance I would ever notice something like this happening or even seeing it in the logs. So the test suite was actually super helpful here. And this is how the final state of the Rust burst, how they look like. They are working with a real database. They are very like high level and black box. They use some kind of like helper domain-specific APIs for the tests. They communicate with the bot using HTTP requests, so there's like no internal API or stuff going on. They use snapshot testing, so I can very easily update the expected output of the bot when it changes. And yeah, there's like a bunch of interesting stuff here. I have like a separate 1-hour talk just about how I was testing boards. So you can ask about me later, but that's not for this talk. And we actually have a lot of those tests, like over 400. And the whole code base is like 30,000 lines of code. And essentially half of that is just tests and like test infrastructure, which is, I think, pretty cool. Although it has one annoyance, compile times. Like I use async and generics like super heavily in the tests. And it takes like 10 seconds to recompile it on my laptop, which is really atrocious. I didn't really have time to take a look at it yet, but if there is anyone within this audience who is like has the knowledge and time to take a look, consider yourself being nerd sniped. So that was the implementation and testing on boards, but we also needed to like actually ship it to production, right? That's like the most important step. So we created this tracking issue to kind of track what is going on there, and it was actually quite many things to port it. Because it wasn't just about switching Homu for boards one-to-one. We needed to like get rid of a lot of tech debt in our infrastructure, which took a lot of time. So for example, I went through over 200 GitHub repositories of the Rust-like organization, and I tried to like get them under automation, which meant putting them into our team repository, which is some kind of like infrastructure as code way to manage our repos. And then we could actually go and migrate from Homu to GitHub merge queues for all the other repos other than the compiler repo to make the whole migration process easier. Then we also had to like deal with some legacy stuff. For example, for some historical reasons, all the main CI of the compiler was running on a completely different GitHub organization. Like, don't ask me, just historical thing. This took us like few years to like untangle, and it was kind of required to land boards. Otherwise, we would need to implement support for multiple orgs, which wasn't really needed. Then we also had to figure out like how we will run Homu and boards inside the same repo. So we came up with this like boards2 prefix to distinguish those two bots. Here you can see the try builds in action. So it tries some CI job without merging the actual pull request. And this allowed us to actually implement new functionality which wasn't possible in Homu, which was like quite nice. So for example, this arbitrary try builds allowed us to say like, hey, I want to run this specific CI job on the PR. And that was like quite useful because Homu couldn't do that. Sadly, this specific pull request was actually a kind of a fail on my side. I managed to broke the CI of the compiler in a very funny way. And what happened was that essentially all the PRs were getting merged without running any tests. So I think I might be holding the record for like the most PRs merged within the span of like 1 hour, because just like everything in the queue got merged instantly, and then the infra admins had to like go and force push the old version. So yeah, that was a lot of fun. After some time, we were like confident enough that we can actually switch like the normal boards try command to be implemented in boards and not Homu. So we did that in 2025. And this required doing a very sophisticated and surgical change to Homu, which essentially boiled down to commenting those 4 lines of code and then kind of redeploying and praying that it will be still working, and somehow it was. Then we also had to actually implement the merge functionality. Ironically, this was one of the last things implemented in boards for some reason. Luckily, we had a Google Summer of Code project in 2025, where Sakibul did a lot of great work. He implemented the merge queue, the merging process, the rollups functionality, the web interface, and then he became a member of the boards team. So that was really a great piece of work. And at the end of 2025, I thought like, hey, we are getting near the end. We can really land this finally. So I did like a little Christmas sprint where I tried to like figure out all the remaining edge cases, race conditions, bugs, and really get this over the finish line. This required implementing some functionality that was only used for the porting process, just for 1 day, essentially, just to move it from Homu to boards, and then we got rid of it. I also implemented some backwards compatibility stuff. So Homu, when it posted these comments, it actually had, like, in a HTML comment, it had like a JSON metadata that was then handled by other Rust bots, and we had to re-implement that. Fun fact, the metadata is still using the Homu name because it was like easier to use the old name rather than to change everything. So yeah, that's backwards compatibility for you. And then at the January 7th, I was finally done. I was confident that it will be working. So we finally got the first pull request that was merged with new boards. So that was great. However, that wasn't really the end of everything, because we still needed to do like a bunch of cleanups, like remove legacy compatibility stuff, update documentation, update all the other bots that were working with Bors, and so on. We also ran into some fun issues. So this was the last PR merged by Homu. This was the first PR merged by Bors, by new Bors. If you notice, they actually have a different like committer email address. Now, it didn't even like cross my mind that this could be like an issue. I didn't think about it. Like, surely no one would hard code the Bors email and like do any sort of the decision based on it, right? Well, it turns out that it was actually load bearing in like a bunch of places that were depending on the exact same email committer or committer email. So yeah, that was fun. I first tried to fix those places, then I just gave up and just like modified Bors to use the old email because it was just simpler. So finally, after all that was done, we could like declare victory and say, archive the Homu repository and just start using Bors for everything. Now, even though we had some issues with the Homu implementation, I think it was actually pretty good. Like it was working for almost 11 years. Across the compiler repo and the subtrees, it emerged like over 70,000 PRs and almost 300,000 commits. So I think that it deserves a round of applause for its service. And so what is the result? Well, I am biased, but I would say that the new Bors just works. Like, it kind of became boring technology, which is exactly what I wanted. We no longer need to think about it. We don't need to like babysit it. And this is especially important because, as you might know, like GitHub it wasn't really feeling well in the past few months, and Bors doesn't really mind. It just like has all the complicated implementation, all the tests, which allowed me to handle with these race conditions, and it sort of just works. I think I fixed like 2 or 3 like small edge cases and bugs since January, but other than that, it was like working. I don't even want to imagine what Homu would like do with this kind of state of GitHub. And we are even able like to finally implement some new features, like this visualization of PRs within a rollup, or this progress bar at the top left of like the current CI job. So that's quite nice. And there is still a lot of things to implement, but the main thing is that we can now do it. Before, it was like intractable to add new features, so this is pretty nice. Finally, I would like to thank a bunch of people. Those 2 contributors in particular. Long did a lot of work to implement various features in 2024. And then, of course, Sakibul, in terms of his GSOC project last year, implemented like essentially the whole merging functionality, which was an enormous piece of work. I would also like to thank the Rust infrastructure team, because they did a lot of like changes and improvements to the Rust infrastructure that even made it possible to change the Triagebot implementation. And finally, also everyone who ever contributed to Bors. So I actually extracted the Git statistics from like the Homu, Bors, all the forks, all the versions back to Graydon's original version. And it turns out it is more than 100 people who ever like committed something to Bors or Homu, which I think is pretty cool. So I would like to thank everyone mentioned here for making Bors possible, and for enabling it to do the hard work of merging PRs, so that the rest of us humans can focus on what we love to do the most, and that's improving Rust. So thank you.
Thank you, Jakub. It's incredible that you got that detailed a talk out of a simple weekend project. You must be very proud. All right, do we have some questions?
Well, thank you very much for the talk and for working on the new Bors. Now that there's a new Bors, what do you think about giving it a new profile picture? I have some suggestions already, which you might remember from last year.
I actually have one image from Mara in my Tulip DMs right now, so I was thinking of maybe we could do a contest at the all hands, like vote for the most popular. Yeah, we should update the profile picture.
Yeah, vote for the best fish picture.
Yeah.
Anyone else? Oh.
How easy is it to enroll Bors into other projects other than Rust, in other languages even?
So it is implemented in a way where it is pretty easy. Like it has support for multiple repositories and everything. But I explicitly don't want to support that because we kind of like the infra team is already kind of like stretched in around the like maintenance, And I don't want to build a project that will be used by anyone else really, because then people would come and like ask to add features and stuff. And also like we added a bunch of features that are like only for Rustling Rust. It doesn't make sense anywhere else. And this allows us to keep like like hard code certain things, which is much easier in the code, rather than like for example this determining permissions for who can merge stuff. It uses our own internal Rust database. Like if it was like a general project, it would have to be like some abstraction of like how to get the permissions and like SSO or whatever. So yeah, I kind of want to avoid that. So yeah, I mean it's pretty easy to fork, I guess, but I really don't like. I told this to a bunch of people. I don't want to like maintain it for other projects. So sorry.
Hi, thank you for your talk. As someone who has also implemented a merge bot and regretted every bit of it, the Bors NG project largely ended because of continued quirks with the GitHub API and pull requests not getting marked as merged and such. What advice do you have for people facing that?
So I really think that the thing that helped me the most was the test suite, right? Like really, testing everything in an environment that is as close to production as possible. So don't mock anything. Test like all test the real database. Have a way to like interleave or test all the possible interleavings of the async stuff. To test all the race conditions. Like I have tests that really like there are tests that like have a specific GitHub issue that happened like once, like some months ago, and I knew that there was like this specific interleaving of like things that happened, and I can test that because of the effort that we put into the tests. So that's a big difference from our other bots that are usually like they don't have almost any testing, and I think we have many more issues with those because yeah, we don't have the tests. So that's probably the number one thing, like write it in Rust and have really good tests.
Thank you.
We are pretty much at time. If anyone has a one-sentence question and answer, yep, I will. Let's see if we can get to you.
Do you know where the names Bors and Homu came from?
I actually have no idea. Which makes it like sort of magical. But I'm sure someone here knows.
I'm sure they just are. Once again, thank you very much, Yaku, both for the talk and for the work.
Thanks.
All right, we have a 10-minute break, so if you want to change rooms, A, you are incorrect, but B, you can do so. And we'll see you in 10. All right, welcome back. We're going to make it extra difficult for the people still going up the stairs to find their seats because the lights are going out. Good luck. Next up, we have, in the long tradition of Are We X Yet subjects, today it's going to be Are We Interop Yet, which is going to be presented by Teor. They started using Rust and C++ Interop in 2018 at the Tor project. They joined the Rust Foundation in 2026, which I believe is still this year, to work on Interop in the compiler and tooling. And Teor has the very dubious honour, I believe, of being the most jet-lagged speaker, having travelled 33 plus hours and crossed 8 time zones to be here. So hopefully Teor manages to stay awake through this talk, and let's give it up for Teor.
Thank you. So, are we Interop yet? The answer is it depends, which is the law of Are We X Yet talks. So, just to give you an idea of what I'll be talking about today, this is a bit of a quick talk. So, a bit about me, talk about the Rust Foundation Interop initiative, the trouble with C Interop, different Interop tools that people have been using, and the next steps. And then afterwards, if we have time for questions, I'd love to hear questions, but also if people want to say what their Interop priorities are, very interested in that. So, started working on Rust in 2018 when I was working for the Tor project. They were experimenting with Rust parsing untrusted data, which is a very popular use for Rust because when you parse untrusted data in C, you tend to read or write things you shouldn't. Then started working on C++ Interop in 2020, was working with some manual C++ and Rust bindings, but also we had some automation with the bind gens and with CXX. And then started the Rust Foundation earlier this year to work on interop problem space mapping. So the idea is to make a list of the problems people are experiencing with Rust and C++ interop, and then write down the things that people have already tried and the kinds of code that runs into those problems to avoid having to go and research that context again when we go on to try and solve the problem. I've also been working on a Rust compiler experiment. One of the interop features that some people want in Rust is function overloading. So C++ can do it. Rust, well, it depends. And so we've been experimenting with making overloading more ergonomic in Rust. And we have an outreachy intern that will be helping to work on that project. Also, as part of that, we had a bunch of outreachy applicants write code examples for Interop, and that turned into an informal user study. So we have, I think, 10, 15 PRs that show what first-time Interop users experience when they go and try and write Rust and C++ together. So that, I've still got to sit down and analyze that, but that'll be a good thing to see the kinds of issues that people run into when they try and start to build Rust and C++ together. Yeah, and that's my GitHub. So the Interop initiative is a Rust Foundation initiative funded by Google to try and improve Rust and C++ interop. What I've been doing as part of that is coming up with problem statements and tracking use cases. So the kinds of things that people want to do with interop, talked about overloading and building Rust and C++ together, but there's also things like safely using references and tracking lifetimes and ownership. And part of the goal of the project is to link and prioritize these different use cases and problem statements together. You can go to the Interop Initiative repository, have a look at the tickets, and have a look at the problem statements so far. One of the other things that we've been looking into is They're targeted changes that we can make to the C++ standards in order to improve interop between the two languages. As I said earlier, looking into the overloading in the compiler and seeing if we can improve the ergonomics of that, and looking at the build system and seeing what kinds of problems people run into. But it's not just those things. There's also, I think, over 20 project goals for the Rust project that are somehow related to interop. I was going to make a list, and then when I got up to 20, I thought, well, that's not going to fit on a slide. So there is a lot of work going into interop, not just with C++, but with a bunch of different languages. So the trouble with C interop is that C is everywhere. So whenever you go to bind to system libraries or another library, you're often going through a C interface. That includes networking libraries, security, user interfaces. And a lot of interop is specified in terms of C and C features. APIs, binary interfaces, linkers. Everybody goes to the level of C to specify how things behave. It's so dominant that we often don't even think of working with C interfaces as interop. C is another programming language, but it's the programming language that a lot of other languages work on. So yeah, we don't even think of it as being interop. But there are a lot of features that C can't fully capture because it's, what is it now, 40 years old? So the big one, memory safety. Ownership, lifetimes, destructors. C doesn't really have a concept of those things. You can document them, you can name functions correctly, but the compiler can't check them. Some other examples, generics, which Rust and C++ and a bunch of other languages can do. Overloading, which C++ can do, but Rust can't quite do as much. Inheritance, templates. Concurrency is a big one. So it's very hard to encode concurrency invariants in C APIs. But Rust and C++ both have strong concepts of concurrency. So if you're writing everything in terms of C, you kind of lose that information when you drop down into the C bindings. And a bunch of other things as well. Might even be easier to list what you can capture in C-based interfaces rather than trying to list all of the things that modern programming languages do that C can't do. So people have come up with a bunch of different solutions to try and create bindings that contain stronger information about ownership and memory safety and a bunch of other language features. And so there are a bunch of different tools and different approaches to that level of interop. For example, one of the newer tools is Zynga, which tries to create interop between Rust and C++. And their philosophy is that since C++ is a more expressive language, you write your bindings in C++, and then it'll automatically generate your Rust bindings. Crewbit from Google has a slightly different philosophy where everything should be able to interop automatically. So they will have a look at the Rust and the C++ code and automatically generate bindings for it all by hooking into the compiler. And it does use a lot of Rust unstable compiler features in order to support that. CXX, one of the older tools, has a goal of having safe language interop based on similar language semantics. So where there's common semantics between Rust and C++, it will generate bindings for you. It also comes with a library of types that help bridge the gap between the two languages. AutoCXX, which is based on top of CXX, tries to automatically create CXX bindings for you rather than you having to write them manually yourself. And then some of the older tools, BindGen and cBindGen, will create, based on manual glue code in both languages, but help you create those bindings as well. But Interop isn't just about Rust and C++. There are a bunch of Interop tools that help Rust interop with other languages. This is a bit of an older list, but yeah, I think there's about 20 tools on that list, too much to cover here. So, what's next for Interop? The problem space mapping. The goal is to list out a bunch of problems and use cases, and then identify some high priority problems and go into them in detail. If possible, have a look at some high impact changes to the C++ standards that could help with Interop. Work on the overloading experiment, improve the ergonomics and the diagnostics there, as well as finishing the core implementation of the overloading experiment in the compiler. And we'll have an outreachy intern to help with that. And then once the experiment's in the compiler, we'll have a chance to see how the Rust trait overlap rules impact overloading. So C++ has some fairly complicated rules for resolving overloads. We want to know if we can get away with using Rust rules for trait overlaps for overloads, and whether common C++ interfaces will work with that. And yeah, make it easier to use, make the compiler guide you towards better solutions when the code won't compile. And also as a next step, looking at build system interop, so that first experience of someone adding Rust to their C++ project or the other way around. We'll sit down and summarize what we discovered in the user study, and improve the experience, maybe by making changes either to compiler or to cargo or some other tooling. And yeah, very open to feedback. So if there's any things you want to see in Interop, now is your chance to mention them.
Okay, we have about 90 seconds, so if you would like to interop with this talk, please raise your hand and we will try and get a mic to you very quickly. Any questions? Yep.
You mentioned there are planned changes to C++ that will help Interop. How far did it come yet? I mean, when should we expect those to land?
That's a very good question. So there's a lot of different C++ compilers, and the C++ standards process is quite a slow process. So the goal is to find changes that are high impact and easy enough to implement so that they actually get done. Because the standards aren't really mandatory, if that makes sense. Different compilers will opt out.
All right, we actually have a short break, so I'm going to call it there, but I'm sure Tio would be very happy to talk to anyone about anything to do with C++ Interop. So once again, let's please give them a hand. And we'll be back in about 5 minutes. just let Jonathan turn the lights down and we'll get going. Okay, after that quick break, we're back with the next talk about Rust semantics and GPUs. Mikhail, or as many of us know him, Fractal Fur, works on the Rust GCC backend and likes to get Rust running on obscure platforms such as Game Boys and Temple OS, which are extremely similar. So on that note, we're going to talk about a different platform again, which is GPUs. Please make him welcome.
Yeah. So my name is Michał Kostrubiec. I was introduced. I'm a Rust compile engineer. I like running Rust on weird platforms like Temple OS. I bootstrap Rust C with GCC, and I work at Vector trying to improve Rust support for GPUs. But before I go into like the issues and the current state of things, I first feel I need to quickly answer the question as to why. So the reason why we want to run Rust on GPUs is that the GPU code is usually written at dialect of C++. And people use raw pointers there. It's massively parallel. GPUs have like 13,000 threads running all at once. So you have a lot of room for synchronization issues. And additionally, the GPU tooling, for example, the GPU standardizers will not catch things like integer overflows or floating points cast out of range. And those are things that Rust kind of solves. But for me, the primary reason is just like I really, really like Rust, and I want to be able to write more code in Rust. And I feel like for all of the fans of Rust here, that's like enough of a reason. We want to be able to do things in Rust. And the current state of things is actually, even before I kind of started working in this space, was already surprisingly good to a lot of people I feel don't know. For example, CUDA already supports things like core and alloc. There are some limitations there, but it was already kind of supported. I have worked on removing some of those limitations. And I have also worked on improving support for a lot more stuff. For example, at Vector, we have an internal wrapper on the CUDA runtime, which allows you to run standard Rust code on a GPU. So you can, for example, do I/O networking and all of that stuff from GPU threads. And yeah, so all of this is like kind of work in progress, but we have gotten even multi-threading with like the standard threading API working. And I want to stress this is normal Rust code that was not designed to ever run on a GPU. For example, we got the Rust guessing game. If you have ever learned Rust, you probably know that guessing game, we have got that to run on a GPU, like quite a bit more code. And this is kind of the direction we're trying to go. We are trying to make Rust on GPUs as capable as possible. But when you are doing silly things like this, then you quite often find things that don't work, or like we have reported a lot of bugs to NVIDIA, or just silly semantic mismatches. And now we'll go kind of over address spaces. A lot of you may be already familiar with what address spaces kind of are, loosely. They're very nice to have in the land of CPUs. So for example, you can use them to distinguish between user space and kernel space pointers so that you do not mix them up. You can use them for memory map layout, and on targets like AVR, they can be very useful for some optimizations. So the AVR is a Harvard architecture, so you need to use different instructions to load data embedded within your code. And this is a bit of a problem because, well, your pointers, they all point to the data space, so how do you load data from there? So ALVM solves this by copying those constants from the constant address space, so copying them from your ROM to your RAM, and that kind of wastes space, that wastes time. But I still want to stress that in those cases, the address space is an implementation detail. It's like something that will improve the experience, but it's not something that you necessarily have to interact with. But in the world of GPUs, the situation is quite different because they have a complex hierarchy of address spaces. And you have something called a generic pointer, which can point to any of those address spaces, but I would like for you to imagine this kind of as an enum of all of those different types of pointers. And this is a leaky abstraction, so you will still have all of those weird semantics of every single one of those address spaces leaked to you. You kind of pretend that they don't have those different semantics. And I will first start with the CUDA shared address space. It's a small chunk of memory which is wired to a CUDA core, and this means that it's very, very fast to access, 100 times faster than like the normal global GPU memory. But it has the downside of having no initializers, so that's something we have to like figure out how to represent that within the semantics of Rust, that sometimes statics can have no initializers, and it's what we call block local. So only a certain set of threads which are running on that specific CUDA core can access that memory. And this wreaks havoc on the semantics of Rust because it means that references are not send. And Rust assumes that references are send. And this is less of an issue for this particular address space because this is opt-in. You have to put something in this address space. And it's kind of the spoiler for them. Not using it will still give you a performance hit, but you can try to not use that, which is not the case with the next address space, the local address space. So as the name suggests, this address space is thread local. And CUDA decided to place your stack there. So that means that all of your stack references are not sent. We will have an example with the standard API we like exposed on a GPU where like you try to send a reference to a stack already the atomic, and this will work on all CPU targets, but this will break on GPUs. This is an example where the STD basically can also do that without STD. It's just like a simple, convenient way to explain the issue. And here the question is like, what can we do about this? One idea is to emulate the stack, move it to the global memory, but this has some like overhead, and this is not really well supported, and it requires people to change the way they launch their kernels within Rust, which is a slight incompatibility, and this is something we may also want to avoid. Besides other spaces, there's also another thing that's very GPU specific. It's called convergence. So probably nobody in this room has an idea what convergence even is. So I should first explain kind of how GPUs work, because the idea of a thread in the GPU world is kind of a misnomer. Really, it's more similar to an SMID lane. So all of your threads are grouped into something called warps, and all threads within a warp, they execute the same instruction in lockstep. So here we first want to add two numbers. So all of our threads in that warp, they do this all at once. And if you have control flow, the threads they go to sleep. They get masked off, so you can think of it, oh, a thread goes to sleep when it's not supposed to be doing work. But then they wake up and they still are executing all of this code together. They are in lockstep. And you may think, oh, this is a quirky implementation of detail, GPUs are so silly. But this is actually exposed to you via some GPU intrinsics. And this may seem like a very stupid idea. Why would you want to expose this weird execution model to the user? So this can actually be used to write very, very performant GPU code. So here I have a very simple example where we pick one of the threads within a warp, the thread 0 to be the so-called leader. And instead of having each and every single thread load the same value from global memory, we have all of them, we have the first thread load this value once and then broadcast it to the whole group. And you can use those intrinsics to not only do simple things like this, you can use them to do things like rolling averages. You can use them to do faster matrix multiplication. Any use case in which you are fetching similar data from this set of threads, group intrinsics can speed up, but you can still not see any issues with this. So I would implore you to think about what happens if the thread number 0 here is sleeping while we are trying to do this broadcast. So what I want you to think about is like really those intrinsics that are sensitive to control flow. Here I have an example in which we try to elect a leader, this time not hard-coded. Amongst the currently active threads, we try to select one of them to perform some operation. And here we have an if with two identical arms, but those arms will still behave differently. Because the set of threads in the first arm and the set of threads in the else arm, they will both elect one specific leader for that group of threads. And the thing is, this means that this intrinsic is sensitive to control flow. So that's what we call a convergent function. A convergent function is a function which is sensitive to control flow. And the compiler doesn't know that something like this exists. And you may look at this function and be like, oh, those arms are identical, and the compiler looks at this and may say, oh, identical arms of an if. Why is there even an if? I will optimize this away to this. But there is a difference in behavior here that the compiler doesn't know about, because instead of electing two different thread leaders for different groups of threads with very different behavior, we are now electing one leader for both sets of threads. And this is very problematic, because this is a difference in behavior which can be observed, which is a misoptimization between like a debug and release, and it also breaks a lot of GPU algorithms which are designed to take advantage of this convergence stuff. So you may think, oh, that's kind of bad, but it gets way, way, way worse, because convergence is what we call viral. So if you have a function which calls a convergent intrinsic, that function is also convergent by its very nature, because it's also sensitive to the control flow. If you have like an if, like the one I showed you, above somewhere in your call stack, even if the compiler changes that if way above, like tens of the stack frames above you, this will still lead to an observable difference in behavior. So really this means that you have to take care of convergence all the way to your call stack, to the moment you start caring about convergence. And One solution we think about is like, oh, can we just disable our mirror optimizations, or can we disable some of them? Try to make them convergence aware. Can we decide which optimizations are allowed and which one of them are not allowed? But the big problem is they're like, we have to answer this question, like, which optimizations break convergence? But that question leads to yet another question. What even is convergence? Because like convergence is not clearly modeled in Rust. We don't have any semantics for convergence at all. So answering the question of like what semantics are broken is impossible if you don't know what the semantics you are supposed to have. And there is another problem here. Like, will any future mirror optimization have to care about this whole convergence business? This is, as I said, this is something very GPU specific. So the question is like, do we want the people who are writing mirror optimizations to have like, I don't know, ping all of the GPU people? Do we want them to have to learn how convergence works for them to be able to write CPU optimizations? And all of this leads to this little line in the current documentation of those intrinsics that they are provided on what we call best effort basis. Meaning that really they may work, they may not work, and you are kind of, we will try our best to make them work, but we will not cry too much if they are broken. And as you can imagine, this is not very imperative to writing good and reliable code, and this is really not the way we tend to do things in Rust. So one solution here is to try to come up with some kind of intrinsics for convergence, and there are a lot of trade-offs, some way to represent some semantics for Rust. And there are a lot of trade-offs here, and I would think that the main trade-off really here is we don't want to like annoy the CPU people, and we don't want to like give Ralph a heart attack by introducing some really weird things to the semantics of Rust. So one idea I have been kind of toying with is, can we limit the notion of convergence? Can we take all of this nasty GPU-specific business and put it into one nicely shaped GPU box where all of the CPU people can pretend, oh, this doesn't exist, and we don't have to worry about this too much. So here I have an example like semantics I've been toying with, where we have the people who are writing, who care about convergence explicitly specify, oh, I care about convergence here. I will use this opaque convergent if that the compiler is not allowed to optimize the way it optimizes normal ifs. And this way, it's way easier for people to write normal compiler optimizations, because it's just an opaque intrinsic. The compiler can pretend that it doesn't know what this intrinsic does, and can refuse to optimize just that. So now, instead of having this notion of convergence be spread everywhere in the compiler, we can, as I said, block it off into a very specific place. There's still some pros and cons here. Like, as I said, the big pro is, oh, this is GPU specific. None of the existing semantics of Rust have to really care about this. All of the CPU stuff can stay completely identical. They don't have to worry about none of this, and it's limited to specific intrinsics. And even in the world of GPUs, we don't have to think about all of the semantics of this execution model of GPUs. We can only define how those very specific intrinsics work, and we can this way try to box up this behavior. But this has some cons, and the main, I would say, this is kind of ugly. If you have seen that code, and I think that most people would probably think, okay, this is kind of ugly, and it's a different model from what the GPU programmers expect. So there is a bit of a question, will there be a learning curve for people who want to start writing kernels in Rust, them having to learn that suddenly something like convergence exists and they have to care about it? And this still requires a lot of work to make sure it's sound. I have been like poking around with different Rust GPU people, trying to find holes in the semantics. We have like already discovered some changes, some things to fix some holes we have discovered. But really, even though I would say this is a huge improvement over the situation we had before, where there were no semantics for this at all, and all of this was kind of willy-nilly. It may work, it may not work, but there is still a lot of road ahead. We still have to fully define what convergence actually is within Rust. How will we stimulate it? How would we even maybe check it within something like Miri? One of my things I'm considering is writing after I write out those semantics down, trying to implement them within Miri to be able to see if those semantics actually make sense within the execution model of Rust. I will have to still, of course, talk to a lot of people to make sure all of this works. And so I will start kind of wrapping things up now. And sadly, I have been told that the amount of questions as I can answer is less than zero. We don't have any time for questions. But we have a room at the Unconf wing. So if you are at the Rust All Hands or Unconf on Friday, you can visit us and talk to us if you're interested in GPUs, Rust, other spaces, or conventions. You can also shoot me a message on the Rust-Lang Zulip or to my email, or you can just find me anywhere at the conference. I'm wearing this silly shirt, and you can try to talk to me about if any of this sounds interesting, if you have some questions. And I think I have fit within the time budget. I'm very happy with that.
Thank you, Michal, both for showing us how GPUs are slightly haunted and for being dead on time almost to the second. Very nice work. We'll be back in 10 minutes with the next talk. All right, the door is closing. Let's get into our last session before the next break. Next up, we have Jörgu, who is going to talk about, once again, the GitHub API. So if, like me, you were in the fetal position earlier during Jakub's talk, please prepare to re-enter it. But we're going to talk about it this time in the context of Triagebot, so please make him welcome.
Thank you. We in the Rust project have a bot called Triagebot, and I'm going to talk about how we use it to improve our workflow. But first, a little bit about me. I'm a Rust contributor since 2021. I've been a member of the compiler team since 2024, Triagebot team 2025, and 2 other teams joined recently. I want to start with a simple user journey. So imagine you have someone that wants to enhance the compiler, and it creates a pull request to the compiler. And unfortunately, CI fails. And for that, we are quite good. We have a bot called Rust Log Analyzer that tries to be helpful. And it has 2 links. A web link that you can also access down in the comments directly on the link or the view details. And what it does, it redirects the person to the GitHub logs viewer. And here you can see all the logs from GitHub. Unfortunately, we have a lot of logs, like 20,000 lines is not uncommon on our CI. And it just loads forever. That's an issue. So what you might do is go back and try the plain link. And it works. Maybe. No, it doesn't really work, actually. It doesn't do any formatting at all. And you can see that we have a lot of formatting. And so that's why we introduced in Triagebot a logs viewer. It's accessible via the plain enhance link, and it basically does formatting. So it downloads the raw logs from GitHub and processes them to show them cleanly. But most importantly, it loads them in 3 seconds, not infinite, which is good. Obviously, it has some nice features like GitHub Ads with automatic scrolling, so you don't have to scroll manually to the bottom. Very useful when you're on a phone and you can't easily scroll down. We also have highlighting. So in the project, we often see failures that we want to share to other people. So it's kind of useful to just select one line. I don't know if you can see it, but the middle line is been selected here. And you can easily copy-paste the URL link. Obviously works on multi-line. Control-click on the second, next line you want, and whatever. You can also share it. And so, continuing on our user journeys, so the issue has been identified, fixed, there's a push that has been sent. But now you might want to see what has been changed, both as a reviewer, but also maybe as the author, to make sure that you didn't send unwanted changes. And for that, you may want to use GitHub Compare. So when you push some commits, or some changes, there's a compare button on GitHub, and you click on it, it goes to the compare view, you can see your changes, you can see here that there's 8 changes, it works fine, except in one scenario. If you have a PR where you change some commits before, or even change the base of the commit because you had merge conflicts or something like that, then it doesn't work. 500 changes can tell you the PR author didn't change that much. And what happens is that GitHub Compare does a git diff. And for that, it selects the base of the branch with the head. And in this example, there's feature and feature prime, which is the new version of the PR. But the problem is that there are extra and unwanted commits in the middle, since it goes to the first, the fifth, the sixth, and then the branch. And so that's where all the unwanted changes come from. And so Git has a solution for that. It's called Git range diff. And the way it works is that it compares the previous diff, so the before the new push, and the one after that. So there's two diffs, and it diffs them together. So it's a diff of two diffs. And so that's what we added in Triagebot. And so here you can see a simple example of two diffs with the first range, the second range, and we diff them together, which creates a sort of weird thing where you have a removal of an addition. And after that, you have an addition of an addition. If you don't understand it, it's not unexpected. I sometimes myself try very hard to understand them. But the basic gist here is that the previous version added this line, but the new version actually switched to this block of code. And so in Triagebot, we detect that automatically and post a comment with a helpful link directly to the range diff. And so viewing push changes is great, but it doesn't solve all the use cases. For example, if you didn't push any changes that rebased it, you may still want to access them. And so if you started reviewing a PR, you still might want to see the changes since the review. And GitHub doesn't really have a solution for that. They have a view review changes, but it only goes for the changes that you already reviewed, not the changes you might want to review now. And so that's why we also introduced a view changes since this review link. And it does three things. If there are new commits, and only new commits, it redirects the user to the file change view. So on GitHub, there's you have the PR, and at the end, you can see the file changed. And in here, I don't know if you know, but you can select the commit you want to see. And so that's where it redirects you. But there's also the compare view. So if one of the commits was modified, we redirect you to this view. And if the base changed, then we redirect you to what I showed you earlier with the range diff. And since a few weeks ago, we also support it on review comments. So here is a link, and it only showed if there isn't any body in the review. So here it's just a review comment with no body. And then after many push, exchanges, reviews, you might end up in a situation like this, where you have a bunch of comments, like here are 188 comments. And GitHub can be helpful, but not so much here, where you have more than 100 items that are hidden. And you might try to click on load more, and if you expect it to load all of them at once, good luck with that. It only loads 50 of them at a time, so you have to click 3 times, and of course it scrolls, so you have to click and click and click. Yeah. And so we actually added a comment viewer in Triagebot. So you have the view all comments link in Rustlang organization that is automatically added for PRs or issues with more than 25 comments. And it redirects you to a similar-ish interface as GitHub, where we display all of the comments. Pro tip, if you are in old issue, the link may not be here, but you can just copy-paste the URL above to get access to it. It works the same way as GitHub, just the base URL is not the same. And most importantly, it loads the entire conversation without any extra or unwanted clicks. It's just a whole conversation at once without any leaks. And and then when implementing this, I learned that people wanted to search in old issues for specific comments. And so I made sure that not only could they search, but also that it worked in hidden comments. So here, there's a small example. You can see that the 3 review comments are both hidden. But if I search for something that is in one of them, it automatically opens up. So it will show you directly the one in it. And thanks to Jakob, we also now have a review threads page, tabulation on the side, where you can see all the reviews that have been started. And while here it's not as useful, it can be very useful on RFCs, where there are many threads with different comments, discussions, and you can click on one and it will go right to the one you want. And surprisingly, it works even when GitHub is down. We had multiple incidents, well, as you know, and as long as the API works, we work. So I'm quite proud of that. What's next? We don't have much things planned. We based ourselves mostly on what the user of the Rustlang Rust wants. So if you have any ideas of things you might want, things you think should be improved or whatever, feel free to tell me. Thank you.
Thank you very much. That is super cool. I'm looking forward to using some more of that. We do have a few minutes for questions, so if anybody would like to ask any questions, please raise your hand and one of us will run a mic to you. Okay, you're going to go? All right. Just while Jonathan's getting there, is anybody else going to raise their hand as well? Okay, I'll come to you.
Hi, yeah, that looks awesome. I had a question. GitHub semi-recently upgraded their search. Well, not very recent, but you have search across issues. Was that, did it not include the hidden comments, or why was it necessary to include your own search across comments? Thank you.
GitHub search can help, but the use case I was told we had was we know in which issues we have specific comments we want to look for, but there's no search engine for a specific issue. So you can search across many issues, but if you know which issue it is, then searching inside, even with the native browsers like Control F, doesn't really work with hidden review comments.
Hey, during GitHub outages, does the API generally keep on working? And did you ever consider caching the results and saving them in the database, so for better load times and resiliency?
Most of the times the API works, but we still have small cache for things that are accessed many times. So for example, for the comment view, we have 100 issues that we can store at a time. So most of the ones that are accessed fairly regularly are being kept. But we also have that creates issues with consistency, so we have to bust things and that sort of things. But yeah, we talked about having everything in a database on our side.
Is this on? Yes. Okay, thank you for this awesome talk and also for this awesome tooling. This is more of a question for the whole audience, not directly to you. I feel like this is the third talk now where we have tooling to work around GitHub's shortcomings. And maybe we should, as a community, think about that. I'm not suggesting anything, but I'm kind of feeling the sense that GitHub is not a solution to a problem that we have as a community anymore. Thank you.
Yes,
I had a question since, in like the same vein as the previous one, a lot of this seems just duct taping GitHub. Have you just considered leaving GitHub? And I know that you abandon a lot of like conversations and discussions, but with the recent backlash that GitHub has received, have you put any thought in just leaving?
Yes, but the big issue we have is CI. I don't know if you've been on Jacob's talk, but we have more than 3 million minutes of CI every month, and we don't have currently the capacity to go anywhere else if we had to pay for it. So we're kind of stuck-ish on having it. We're hopeful a little bit that GitHub will be able to improve the situation in the next month or so. So we'll see how it goes. And also, even just switching to another provider would mean that all of our bots would need to migrate. And that's a multi-year project because we have many bots, many integrations, the release process, and all of that currently relies quite heavily on GitHub.
What is the hardest or most annoying thing you have to implement when in one of these?
Let me show you. So on the range diff here, GitHub doesn't have anything to do range diff. So we fetch the previous version, the new version, and then we have to compare them next to each other. So we basically do diff of diff. That's pretty easy. But then there are many unwanted changes, like context changes. If you see here on the slide, there are lines where there's nothing, no plus, no minus, or whatever. And sometimes there are changes in that area, but they don't impact anything because they're not relevant. And just doing filtering on this is pretty non-trivial to be able to show it correctly afterwards, because you have to take context lines before, after, and all that. So kind of a big logic to do.
Hey, I don't have a question, rather a partial answer to those that say why is GitHub doing nothing or apparently nothing. They do try to respond to feedback because, of course, we are not the only ones having these issues. We have a communication channel with them. We report our wishes, our complaints, and they take note. So they know that we know, and we know that they know. So yes, it's like that. But they're working on it. Sorry. One more thing. I'm not from the infra team, so I don't know the details. I know that we tried to mirror the GitHub repository on GitLab. At least I saw a pull request flying around about documentation, but I don't know what's the current state. If someone from infra is here and would like to chime in, maybe can give more thoughts about that. But that's all.
Hi, thanks for the talk. If I understand the feature correctly, you update the comment of some other person, right? Is there a liability or risk of changing this, or just some race condition? How do you think integrate that into your solution?
So you mean in this case, for example? Yeah. I wouldn't say about liability, but yeah, some people don't really like that. But also posting a new comment is also disruptive. So we try to make it as less visible, but still accessible as possible. On this slide, for example, there's also the rendered link at the bottom. That's also from us. it depends. Sometimes a new commons is the best thing. Sometimes if you can integrate into an existing commons, we try to avoid it where we can. But yeah.
I, for one, fully support my comments being edited to be useful because half of the time they're not. We are at time. Thank you for being here, and thank you once again for the talk and the tooling.
Thank you.
All right, we now have a half-hour break. I believe there will be some snacks and some drinks downstairs, and we will be back here and in the other rooms at 4:20. Insert Netherlands joke here. Oh, can we get some water?
I will get water.
Thank you. Welcome back from the afternoon tea break. I hope everyone enjoyed their snacks. I know I did. Just before we get back into the program, firstly, you're in the Rust project track. If that's not where you were meant to be, please very quietly leave. Otherwise, we want to mention the Unconf partners who are helping to sponsor the Unconference and the All Hand, Microsoft, Vectorware, and Ferris Systems. So thank you to those three companies for sponsoring. And next up, we have Alejandra, who is going to talk to us about compilation types and incremental systems.
Okay, okay. Okay, so hello, I'm Alejandra Gonzalez, a Clippy team member, obsessed with performance. I also won a Google OSPV award some time ago. I've led 2 break goals about performance because I heavily dislike how when compiling some crates you just have so much dead time. And this is the third. This is the third break goal of this. So today I'll talk about a conceptual redesign for the incremental system. That is the system that manages your target directories, and it also manages like recompiling and stuff. But first of all, let's state the obvious. The Rust compiler is slow, very slow. In fact, I've seen people complain that some package, in this case Vevi, takes like 2 minutes to compile. Yeah, 2 minutes. That's perfect. So this is due to the compiler being very complex, which is a side effect of all the positive stuff we love about the Rust language. So yeah, I forgot to go to the next slide. So borrow checking, trait solving, macro expansion, Rust takes time because it handles heavy concepts. And while we could try making borrow checking faster or try, making some cool algorithm for symbol interning, I think that the compiler now is way too full of micro optimizations, and that we should just compile less Rust at all. So today I'll be talking about redesigning the incremental system so that we can in fact do that, compile less. So this has actually been a redesign that's been marinating in my mind for the last like year and a half. So if you find yourself thinking, hey, I've heard about this somewhere, it's because I've done 2 PRs, 1 RFC, another talk in another whole conference, but today we'll delve deeper and explore more possibilities about this hypothetical redesign. So chapter 1, some context. First, I'll describe the problem, and then we can see how we can tackle it. If you right now go to a terminal and run cargo check and then cargo build, the cargo build will reveal your packages as expected, but it will reveal them including dependents in your local tree, and the target size, the target directory size will be a lot greater than if you just run cargo build in the first place without cargo check. And this is completely unnecessary because many things in cargo build are also computed in cargo check. So why not reuse those? So being that this is the Rust project track, I kinda expect that you know some things about compilers and stages and all the different stages that Rust goes through, but I'll do a very quick breakdown still. So in the Rust compiler, there are 5 different stages, each of them with several sublayers where analysis is also done, linting, macro expansion, all that. They are roughly Lexin, AST, here, mir, and then Cogen. Some notable sublayers are like linting or borrow checking. And also note that this is all very extremely heavily simplified because the compiler stages more or less also kind of look like this. And this is only half of the picture. This is a cargo check on a Hello World crate. So now that we've remembered the compiler stages, I'll represent compiler runs as a series of. Now that we've represented compiler stages, I'll represent compiler runs as a series of nodes connected by arrows. Now we can very clearly see that these two runs are pretty much identical. Yeah. So, chapter 2, queries. One of the main concepts that powers the compiler are queries. Queries are functions that with a cache. That cache is called a query context. So if you have, for example, to compute lifetimes and boundaries checks, it would be extremely expensive to compute them every time they have to be used. So instead, if you have the same input to the same query, it will just ask the query cache, the query context, and return the cached results. So these two concepts can be mixed. We can extract each of these stages into their own query. So if the here doesn't need to change, if the here hasn't changed, the mir won't be recomputed, and thus the code gen won't be redone. Same with AST. Same with AST. Same with mir, here, codegen, everything. And this is something that more or less already exists in the compiler. We are always trying to queryify it more and more, but it's not fully in the compiler yet. So the smart people in the compiler saw that if you queryify the different stages throughout compilation and you serialize the query context into a file, in a sensible manner, obviously, it could be possible for us to save all that information to disk for future compilations, and we could, in those future compilations, reconstruct any given compilation. And that's how the dependency graph was born. So, if we track each executed query and track all the subqueries that that query calls, we can make a graph out of that, like this. So this graph tells more or less a complete story of how any given compilation went. And we can safely write that graph into a file, and most importantly, do that for future compilation reconstruction thingy. So then, with that file, we can check the hashes with the semi-famous try mark green algorithm, which goes node by node, checking if the hash is the same, as expected. Yes. Or reevaluating the query if the original value has changed. Okay, so now all that is explained. We know the problem, we know how the compiler works. Here's where we introduce the hero in our story. Atomic levels and data dependencies. So let's first talk about those atomic levels. And these are little stringy directives that tell the compiler what stage of compilation it should go to. And of course, they also represent what, to the incremental system, what was the objective of the last compilation. So for example, if you just need AST information, we direct the compiler to only compute the AST and then exit. All the queries related to processing the AST would be in the AST atomic level. The same for here, mir, everything. So this way, any compiler adjacent activities such as check or build or clippy could declare an atomic level they'd like to go to. And for example, in this case, while cargo check or cargo clippy go to the borrow checking atomic level, cargo build goes to the emit binary atomic level, and we can now represent neatly in the target directory what was the intent of the last compilation, thus giving more information to the compiler, allowing it to do certain optimizations that I'll talk about later. It also allows us to avoid tying an incremental to what flags are used, so we no longer have to recompile if we only changed one flag. That doesn't matter in the end. So here's where here's where data dependencies come in. While we can extract what stage the compiler goes to via atomic levels, not all information can be extracted that way, because that would just be like redoing compiler flags all over again, and that's pointless. And that's where data dependencies come in handy. So data dependencies are these little bits of information that each query can request and that act like leaves in the dependency graph. So talking about the emitting binary scenario, data dependency could be something like link time optimization or certain macro expansion information, or how the symbol mangling should be performed. So this allows us to move the change in the try-mark-green algorithm from the later stage to the necessary one. So LTO options will not impact Clippy, for example, or cargo check. So these data dependencies aren't only for emitting binaries, they are also value of CFGs or linked information for changing between cargo check and cargo Clippy. And being that these are lazy, as they act like leaves in the dependency graph, we can perform a few optimizations that, if we have time, I'll get into at the end. So, apart from not checking with Clippy for linker changes, that also goes in the other direction, build can jump off the progress that cargo check made, because now that codegen options are extracted from hashing in the incremental directory, we can guarantee with some absolute certainty that emit binary will always overlap with borrow checking, and thus use that information in our current build compilation. So now people are content with their compilation times and everything's fine and we can all go home, except we can, because the thing is that we as programmers do this very weird thing of not only changing compiler flags, we also tend to write some code in between compilations. So we can delve deeper. So two-stage fingerprints. If you work on a big project with many dependencies in your workspace, you probably know that emotion when you change something that's ultimately completely irrelevant, but you still trigger a rebuild. This sentiment is especially frustrating when you see that in your monorepo you have to build a whole branch of dependencies just because you changed a single constant that is not even used that much, or even funnier, like making a comment. So, as you may know, dependencies aren't handled by the Rust compiler. They are handled by Cargo. Cargo orchestrates package compilation so that every package, when it's time to be compiled, can have all the necessary dependencies available. Cargo checks if these dependencies have changed in any way, and if so, they have to be recompiled to have the latest version of our code. So this change in any way doesn't only I'm sorry, I went through something. Yeah, I went through this one, so ignore that. The process that Cargo check follows for rebuilding your dependencies starts in the outermost layers, and Cargo checks if these outermost dependencies have been changed in any way, and if so, these outermost dependencies are revealed. But this changed in any way means that Cargo, apart from checking things like the source code itself, also check things like well, the compiler version, which is also kind of important, also checks the last modified time, or or other useless stuff like enable features. So here's where the second concept of our talk comes in: two-stage fingerprint. Two-stage fingerprints. So instead of compiling all the way to emitting binaries for every changed dependency, we only go as far as to do name resolution. I'll do another quick refresh on what name resolution actually means. And name resolution is the stage in which the compiler actually figures out what those variable names, function names, structures, all that mean in your code. It takes into account modules, scopes, variable shadowing, all that. And being that definitions IDs, def IDs, are calculated on name resolution, if we only went up to name resolution, we could see if those hashes were changed in the dependency were used. Okay, so if we only calculated which items were used in a dependency, then we know if the dependent uses those items, and if so, we have to reveal the dependent, but not always. So there are lots of ways to do this. One is to calculate the two modules to name resolution, and then compare them. Compare if the dependent module depends on any of the modified items of the dependency module. In this model, we take advantage of the fact that the dependent module would have to be built either way, so we're just saving the process of type checking and code generation and borrow checking, everything before name resolution. So that's like the greatest part of compilation, and I think that's really important. But we have another way, maybe better, but definitely more complex, and that is to track the relationships between all items in the incremental of a dependent, write those to a file, and just check that file before recompiling the dependency. This means that we don't have to do parsing or nameres or anything, because all relationships between dependents and dependencies are already declared in the incremental directory. So you might be thinking, how will cargo signal to the compiler to just go up to name resolution? And the answer is atomic levels. We now clap. So that third key concept of the talk, the two-stage fingerprint verification, is just an example of what atomic levels can do. And similar to these ideas I've been giving, the powerful concept of atomic levels has lots of unexplored potential. So now we've reached the end of the talk, where I can claim to be able to complete that in 1 to 3 years. But you know, I said that we have to delve deeper and all that, and they gave me 30 minutes to do my talk. So why just stop at cargo? Why wouldn't any third-party programs also exploit the system? At the end of the day, we'll already let third-party programs hook up to the compiler via Rust-C driver, that weird dynamic library that only Clippy uses and nobody else. So why not let them integrate themselves even more? Some application I can think of right now is Cargo Clippy reusing type information from cargo check, thus completely bypassing having to do type evaluations by itself, because like in between a cargo check and a Cargo Clippy run, the types won't change, right? So, and talking a bit about big projects, they cannot always use cargo. In fact, in the big projects I've seen, they tend to use these very weird esoteric build systems and try to pair them with cargo, and that's horrible, like make or Bazel or back2. I don't know, that's horrible. My condolences. So just as cargo, other build scripts could go up to name resolution and parallelize everything a little bit more. But I don't have more slides, but I can talk a little bit more. So plugin systems, I think they have a great future if we implement this shareable incremental compilation information. WebAssembly is also something that I can think about. And we could also implement how to reloading with user-written code extremely fast, because we wouldn't have to rebuild the whole workspace tree. And I want to thank some people that I don't think are in the room, but if you're either Bjorn3 on GitHub or @page, please raise your hand. They are not here. But yeah, about the RFCs and the PRs and all that, they've been giving me very useful feedback up until that got like a bit inactive. And that's because of the progress part of progress and gratitude. I'm currently, okay, so this has a break goal, and that break goal is currently stuck because lack of funding. I know. So if your company, if you are incredibly rich, or your company is kind of rich, and you'd like to have much faster recompilation times, please talk with me, talk with the Rust Foundation. Let's make this happen so that I can keep working. You have faster compilation, everyone's happy, and So that's it. Here are my socials, my contact, my artist. And yeah, if you see me through the hallway at any point, just try to talk with me. I have much better ideas for everything in my talk. I was kind of nervous while giving it, so I couldn't get through everything. How much time do we had?
Like 7 minutes plus 5 minutes of questions.
Really? No, wait. Because I don't know if you remember, we can do a bit of a narrative callback to optimization number 1. Let me also... Okay, so optimization number 1, filtering and parsing on... filtering on parse and purge data dependencies on unused configs. So I don't think that means anything. That's just an arbitrary string with random characters. But I'll explain it. So macro expansion is very expensive. In fact, every time I profile Clippy, macro expansion is just at the top. So this macro expansion also includes CFG's attributes. So instead of going all the way from lexing to macro expansion until we notice that the resulting post expansion AST is the same, we could just do some sort of CLI filtering, and with atomic levels we could just stop the compiler at that point. Optimization 2, filtering on early and late lint passes before lexing. So the Rust compiler actually has 2 types of lints. One is called early lint and one is called late lint. Early lints work on the AST and late ones work on the here. So one has parsing information, the other one has typing information. So if we're going up to the AST, why should we care at all about registering here lints? Like, those won't be run, and thus we don't have to worry about them. And optimization number 3, do not rebuild if we only changed a Clippy lint. Because the other day I was doing some experiments with my CLI, and turns out that if you do -w Clippy all on a cargo check run, it will also recompile, and that's unacceptable. So why should build or check care about clip lints? That's pretty much it. So yeah, we are done. I don't want to waste your time on rambling.
Thank you, Alejandra. I would also reiterate, I would like to see this work, so please fund Alejandra so that we can have this. That sounds really nice. All right, do we have some questions? All right, I see a couple. You're going to go there. I'll go up that way.
You talked about hot reloading, but I don't really understand how these atomic levels would help, really, because code paths and things change based, like what the compiler actually cares about, what is removed in like mirror opts and stuff, is very dependent on like what code is actually used. So can you elaborate a bit more on how this could allow for hot reloading?
So the part that allows for hot reloading isn't the atomic levels part. It's the two-stage fingerprint verification part and going up to name resolution. Because, for example, right now, if you do some, it's not really hot reloading in the sense that you don't have a dynamic library. It's more hot reloading in the sense of you have a very big interface with lots of functions, and you add another one in a different module, maybe written by a user, something like that. You wouldn't have to rebuild all those functions that haven't been used.
But surely, like, if that function interacts with them in any other way.
Oh yeah, that's why the name resolution part is there. But imagine so we add via macro or something a new function written by the user, written by maybe an API or something. Like we would only have to rebuild the functions that were used in that new module. That's similar to the other project goal named revealed don't no relink don't revealed. So if you know about that, it's kind of similar.
Okay.
So, speaking of avoiding rework and reusing work, I'm told that when changing comments and small lines in your source files, you can often trigger a rebuild of a lot of stuff because you're changing. If you add a command line, for example, if you add a comment, then all the lines under that command are going to change positions, and so the spans are going to change. How do you address that?
Okay, so we've been worrying about that special use case for like 4 years. No, more, since like 2020. So the thing is that it's quite a difficult problem because of panic locations. So if you panic a thread, it will display panic information, even like including its line and column. So if we were to not recompile on comment changes, it would be quite difficult to have an accurate panic location in those panic messages. So like that's a work in progress that I'm not sure if I can say there's a specific algorithm, but we can work on it. We can open a pull request anytime.
Any other hands?
Thank you for the delightful talk. As maintainer of cargo sandwich checks, I've noticed that Rustdoc building is also quite slow, and I imagine that a bunch of this work would overlap with that. Is my assumption correct? And I would love it if you could expand on that.
Okay, so maybe. Logic says that partially, but it probably does. Like if RustDoc shares even just the AST with any other cargo command, it could, well, if it shares any part, it will be faster. But I'm not sure if we are messing with doc attribute expansions, so I'd have to see that like a special case.
Hi. Hi, great talk. I have a question. You mentioned offhand that macro expansions tend to be really expensive in Clippy. Could you elaborate on that a little bit?
Yes, yes. So there's this function on the compiler called fully expand macro fragment, which fully expands a macro fragment. And those are expensive because I have that little detail in one of my, well, in many of my slides. Okay, so see here, lex parse expand here mirror. Note that little arrow from expand to here. The thing is that in the compiler, macro expansions, after they expand, they have to be reparsed and taken to here again. So if you have nested macros, you're maybe parsing, I don't know, 10 levels of nesting, and that requires very various operations with atomics and creating session globals, I think. I know it could be better. It could also be worse.
On that inspiring and terrifying note,
can I add a little detail? Is that if you or any loved one has macro information that you can share with the class, please message me anywhere, because I'm really serious when talking about macro expansion being the top one function with the most instructions in each and every cargo check and Clippy run. So yeah, please improve that, because I don't know how. Let's go.
Awesome. Thank you very much, Alejandro. We have one more talk left. It'll be in about 10-ish minutes. my friend, this is the end. I'm sorry to say. The last talk in the Rust project track is coming from Tyler Mandry. Tyler works on Rust at Google and leads the Rust language design team with a particular focus on language interop and async, and language interop is what brings Tyler here today to talk to all of you. So let's please make him welcome.
Thank you. Hi everyone, I'm Tyler, for those that don't know me. As Adam said, yeah, I lead the language design team of the Rust project. I'm also on the core Rust team at Google. Those two roles inform my perspective in ways that you're going to hear throughout the talk. I'm speaking for myself, not on behalf of the Lang team or my employer. But like I said, those roles do inform my perspective. I'm not a neutral party. My priority here is the success of Rust and the Rust project, and I count myself very lucky that I get to say that here, but also at work. You should take and evaluate what I'm about to say for yourself. I welcome disagreement and constructive criticism, because I think this stuff is really important to get right. Yeah, so I didn't bring like a Google hat to like signify like when I'm like talking more from my Google perspective, but someone gave me these cat ears, so you'll see those. My goal in this talk is to make the case to you, maybe even convince you, that having comprehensive cross-language interop is the best, most strategic move that Rust can make today. But before we get there, let's take a step back for a second. If you look at the trajectory of Rust over the last few years, it's really hard not to be incredibly proud. I mean, in a lot of domains, Rust has become the default language for new projects. Rust is in CLIs, it's in servers, it's in firmware, it's powering a big share of Android, and now it's here to stay in the Linux kernel. Hats off to the Rust for Linux team, by the way. That was an incredible amount of work and persistence, so congrats to them. So we've proven that reliable performance software, it doesn't have to compromise on safety. It's actually changing the way our systems are engineered. Developers want the empowerment that Rust gives them. They want fearless concurrency, great tooling, and performance without the foot guns. All right, that's the good news. Now I have to talk about the bad news. This is a slide from a talk I gave back in 2022. At the time, it looked like Rust might be on this like very steep exponential growth trajectory. Async had just shipped like 3 years before that. We had shipped like non-lexical lifetimes, which made the borrow checker much more accessible. There's like the question mark stuff. There's just all kinds of stuff, and like the uptake was really, really exciting. When I looked back and I tried to plot the dots since then, it doesn't look so exponential anymore. Now it actually Rust has in fact grown since I gave that talk. Like the estimate is like 2x. The source for this is /data, but it actually kind of looks flat over the last couple of years. I looked at a few different reports, including /data, PYPL, and the TIOBE index reports, and they all kind of say kind of a similar story. Like, maybe Rust is like petering out a bit, and these numbers could be wrong. It's not like this need for systems languages disappeared. The same estimates show that the number of C++ users increased by over 8 million, which is like so much. So a lot of these are lagging indicators, and we've been talking about like all this like momentum that Rust has, and I feel it, and I think it's real. I think we're seeing a lot of momentum, especially as people are discovering all of these vulnerabilities and these C and C++ libraries, etc. So I think the demand is there, and I think Rust still has a lot of momentum. It's also still like the most loved language in Stack Overflow's survey every year running. That being said, like regardless of how like true these numbers are, these stories are, I think this is a really good opportunity for us to ask ourselves, as members of the Rust project and the community, a really important question, which is, what does success actually look like for Rust? Like, it's really fun to be on a rocket ship, but like, where are we going? Are we okay with where we are? Have we reached a point where, it's big enough and like we've made our mark on the world? What does it mean for us to actually have an impact? Deep questions. Yeah, thanks. Thanks for coming to the talk. Just kidding. Go to the Rust website. Our mission is right there. A language empowering everyone to build reliable and efficient software. There's something interesting about that phrase, empowering everyone. It doesn't mean everyone in the world has to build reliable and efficient software. It certainly doesn't mean they have to use Rust. But they should have the option, and that's what I want to talk about today. So to understand where we are right now, I like to look at what I call the physics of language adoption. In this model, the language adoption has 3 factors: social, economic, and technical. So the social is like the individual motivation. Do developers want to use Rust? That gets influenced by the community, conferences. It gets influenced by the support that you get when you try to use it. It gets influenced by tooling. It gets influenced by what libraries are available. Big success stories like Rust for Linux. And then we have the economic axis, which is about resource constraints. So if you're a company, can your company actually afford that kind of transition? Can you afford to retrain your developers? Can you afford to take an initial productivity hit while you're actually learning the language? If you're an open source project, can you afford just the time, right? Regulation is a factor here. So if governments are saying, hey, stop writing C and C++, we're not going to buy your thing, or we're going to regulate you, that can be an economic factor as well. And then the final one is the technical. And the technical is just what is physically possible within those constraints, and what trade-offs exist within our control. So let's go through an example to make this more concrete. So this is from a blog post from Android. Shout out, by the way, to Jeffrey Vanderstoep about, sorry, I'm butchering your name, but the title of this talk actually came from this blog post. Interop is the new rewrite, so thanks for that. So what Android did is they improved their security posture very significantly by adopting Rust and reducing the amount of C and C++ that they wrote over time. And we can see the result in this graph. So this is showing the percentage of vulnerabilities that they see that are memory safety vulnerabilities, and it very closely tracks the percentage of code that they're writing that's memory unsafe code, or code in memory unsafe languages. So there's a quote from this blog post that says, quote, "Memory safety vulnerabilities tend to be significantly more severe, more likely to be remotely reachable, more versatile, and more likely to be maliciously exploited than other vulnerability types." So by reducing the amount of new code that was written in memory unsafe languages from 80% all the way down to 20%, they also reduced the number of vulnerabilities that we were seeing that were in this really severe class, right? So this was a success story. And it also reminded us of the other benefits of Rust. Not only did they get the security thing, they reported that their rollback rate for new changes was much lower. I think it was 4 times lower compared to C++. And the review times were 25% faster too, right? So you get productivity benefits, you get stability and reliability benefits. Yeah, Rust is great. We all know, right? So coming back to the physics, right? So in the case of Android, you had all 3 axes lining up. You had the social interest that was there. People in Android wanted to write Rust. I guess not all of them, but there was there's some coordination there. The economic costs of a CVE, of a vulnerability, is really high. Not only do you have to find it and understand it and fix it, and then you have to go deploy it, and that takes time, right? So that actually really justifies the cost of doing this kind of transition. And then finally, you have the technical side, which is well, can you feasibly do it, right? Android is built on it has a bunch of stable C APIs, and then like the rest of the system, that's like kind of at the bottom layer, I think. I'm not an Android developer, but the rest of the system like uses Binder, which is like this inter-process communication layer, and that's all like stable serialized data. So it becomes really easy to just like swap out one component for another, and like the rest of the system doesn't really know, right? So we see that Rust really, thrives in these cases where, first of all, if you have a brand new code base, obviously you can adopt Rust, you can frolic in the green fields, it's great. If you have these inter-process communication boundaries, or of course network boundaries, if you have microservices, it becomes easy. C APIs are like really easy, right, usually. And you can get away with interop across other language boundaries, usually when there's like, it's a small API, like there's not too many types, you can do this. Where it becomes really infeasible though is like tightly coupled code bases in a different language, and maybe you're built on some framework that's like really central to the work that you're doing. So let's say you're like you're a video game and you're built on Unreal Engine, or you're robotics and like you're built on Rust, which is like the big like robotics framework that everyone uses, like things like that. Qt, C-star, like a lot of different ecosystems out there that you can't just like move to Rust, right? Anytime there's a lack of like a central mandate or coordination, that makes it much more difficult. And then like some people have tried to get around this by just like freezing the world and rewriting everything from scratch. That is usually a bad idea for production systems. That it introduces a lot of risk, and production systems generally don't like risk. Some people are saying like, it might change with AI. Like we got this bun thing that happened last week. Like what's that about? We'll see, right? Like maybe it'll all go over swimmingly, but like I don't think it changes like this fundamental nature that you're introducing a lot of risk with new code, and you want to roll that out gradually. So Rust is not the first to encounter this problem and think about it. Swift was essentially built from the ground up for interop with Objective-C, and then later they added C++, because they already integrated into Clang. And so Swift has bidirectional interop both with Objective-C and with C++. Carbon, the language started at Google, and still being worked on there, is also built from the ground up for C++ interop. And this thing makes a lot of sense when you consider just like how big these code bases are, right? Like, hang on, sorry. Google alone has like, does anyone know how many lines of code, C++ code Google has? Millions, billions. Okay, so it's like over 750 million lines of code. So it's just like, it's a lot of code. And so like, the amount of engineering effort that's needed to migrate kind of justifies the cost of looking into like these like language efforts, right? Okay, I'll get back to that. So Rust doesn't have to be the first. We can learn from these examples and from the work that's been done here. So what's in it for us, right? Like, maybe we want users, but like how does that like connect to our mission, right? So first of all, empowering everyone, right? Like it's kind of right there in the mission. We want to make sure that Rust is accessible to like these really big production systems that like power like a lot of stuff in the world today. I think most of the people in here like don't work on those systems because like you're here, right? Like you're excited about Rust, but like a lot of people do. So we're not enabling those maintainers, these like hundreds of millions, billions of lines of C and C++ code in the world. We do have to prioritize, right? Like it's not enough to say, okay, well, we're not enabling everybody, so we should do this thing. So we have to think about the opportunity cost. That being said, I don't see really a bigger opportunity than this for us to further that part of its mission. Maybe I'm wrong. What's in it for Rust? Jobs. Everybody likes jobs. I would like to see more people getting paid to work on Rust, or to work in Rust, and to work on Rust. So I would like to grow the user base for that reason. And that brings a lot of investment back into Rust itself. As companies are able to adopt Rust, or seeing that they're very close to being able to adopt Rust, they will be willing to invest more, and they'll just be incentivized to do that, right? So, yeah, here we go. Yeah, so as an example, like Google, first of all, so the Rust project invested really heavily in a language that would be attractive to companies like Google. So it invested foremost in like a really strong safety story. We had like the non-lexical lifetimes that made it more accessible. We had strong cross-platform story, a really good tooling, supportive tooling, and then we had async. And so like all these things combined meant, Google and other companies were comfortable investing in that language, and Google became comfortable investing a large amount up front. This year alone, Google has committed more than $1 million in contracts and sponsorships, support work in the Rust project, language features, compiler support, etc. That's a lot, especially considering that Google is like in the very early stages of its Rust adoption. So in our internal monorepo, it's called Google 3. That's the one with like the more than 750 million lines of C++. The amount of Rust is less than 500,000 lines. Like it's really not very much. That's first-party code, but it makes sense for Google because like Google can see the benefits it's going to get on the other side, right? Now, not every company is going to be willing to invest that much up front, and that's okay. But I do think that if Rust can leverage that investment to like lower the cost to adoption dramatically for other companies, we'll see like many more companies, like a larger breadth, that are willing to invest because like they won't have to invest quite so much to be able to use Rust. Okay, let's talk about the risks. I mean, yeah, we want Interop, sure, fine. But what are the costs? How can we actually have really good Interop with other languages without making Rust a union of all the languages that are out there that we want Interop with? How do we preserve all these things that we love about the language, the explicitness, the move semantics, zero cost abstractions, et cetera, et cetera? There's a lot of like negative design space, right, in Rust, that things that don't exist that also make it the language that it is, right? So let's not risk becoming everything and kind of losing what makes Rust special. I also think Interop is a superpower. So it's not just about being able to access the users for migration. I think it's a very powerful tool, and I think it would position Rust very well to be a language that every language can talk to, or a language that can talk to every language, right? Rust is not going to be the best language for every use case. It just isn't, right? Like, if you're gonna do rapid prototyping of a web UI, you're probably not gonna reach for Rust. And we can keep adding features that make it better for these different domains, but features interact with each other, and they can increase the complexity of the language in this non-linear way. So plus it's gonna take a long time. We don't want to always try to be the best language for every single thing. I think that would be strategically a bad way to invest our time, right? So what I would propose instead is that we double down on the things where Rust is strong already, and try to make that story really clean and well integrated on all these things, security and parallelism and abstraction and code sharing and crates, and position Rust as the next lingua franca. So that's gonna bring us to our North Star. Originally I thought oh, maybe C++ Interop is the North Star, but no, we actually want to look beyond that, right? To something even farther out, right? So yeah, can we move in a direction such that Rust actually becomes that lingua franca and it has like this central interop rule? I do think a waypoint, that's very important in C++ because it's like, I don't know about you, I think Rust is like a, once in a 25-year kind of language. The last language like that was C++. We need to bridge these two really important languages in the systems space. We want to minimize unnecessary complexity, so we'll take that as our constraint, right? So how are we going to do that? We'll go through a few strategies for how to do that. First of all, delegate complexity away from Rust itself. We already do this with like extension points in the language, like proc macros, with libraries. Interop can do this too. So we've got like code generation, bindgen, crewbit, all the big interop solutions use code generation in this way. We don't need the people working on the language, the Rust language and the Rust project to be C++ experts and also Python experts and also TypeScript. Like, that's not going to happen, right? So we want to delegate as much of that out of the core language and out of the project as we can, but also empower, like, give them the things that they need, right? So that's going to shrink the maintenance burden. Next, just like take what already works in the language and generalize it. So yeah, we've seen like first we had associated types, and then we had generic associated types, and so that's an example of the pattern that I'm talking about. Arbitrary self-types are on their way to being stabilized. We've been waiting. Yeah, field projections, if you went to the talk earlier about that, that's another great example of this. Yeah, so this makes Rust a more expressive language, but in a way that like that we have good intuitions for, because it uses like the idioms that already work really well together within Rust. There's some risk, like we are going to enable more like fundamental things, and like there might be interactions that we don't anticipate, but that's also like part of what makes them powerful. So I think if we do this in a careful way, it can be powerful. Generalizing this a little bit further, so I say design holistically, ship incrementally. This is really just like the Rust project's whole thing. So like, I like to use Rust for Linux as an example here. First they were just like using a bunch of nightly stuff that like, I don't know, we didn't even know about. Like I didn't know about it. And like, they found some way to make it work, and then they needed a few more things, and so we would add those, to the compiler, to the language, and they were just constantly iterating, experimenting, and finally we got to a point where we knew what we actually wanted and what we could stabilize, and so we did that, and then like over time you kind of integrate, all these disparate pieces back into the language, like going back to like generic associated types, like we shipped the MVP, and over time, as we got like the new next-gen trait solver and everything else, like we're going to make the experience of using GATs, generic associated types, like much smoother and feel much more integrated. So like it kind of has to go in this order, because you're unblocking the experimentation and then like creating the value that encourages further investment in the language, right? Design holistically means that you're going to have a working theory of how it all comes together in the end, by the way. But you're kind of constantly iterating on that. Yeah, so sticking to these strategies, it should allow us to support interop in a way that improves Rust iteratively over time. Okay, so yeah, so now I want to talk a little bit about like, what are the actual constraints that the people who need interop are operating under, and I'm going to focus on C++, because I think that's, well, mostly on C++, because like, well, we gotta like get out of the, well, yeah, gotta get out of it. So, all right, let's talk about bugs. What creates bugs? Well, number one, code. The more code you have, the more bugs you have. It's like kind of universal truth. But you multiply that by some factor that I'm calling like the unprevented bug rate. And that's influenced by a lot of things. I mean, your language, first of all, what library APIs you're using, complexity of your domain, in the system complexity and the coupling in which you introduce a new line of code. That also has a big factor. And the other factor is the age of your code. So we know that bugs decay over time, not because they're radioactive, but because we like find them and fix them. And it's like a pretty well-supported result. So I think it's from a Usenix survey, and like you can just see how cleanly that fits. And so like yeah, there's a decay rate, and it has to do with like yeah how quickly you can find them after shipping and fix them. So for memory safety vulnerabilities, I think Android had found that, yeah, after 5 years, you have 7 times fewer memory safety vulnerabilities. They also found that Rust, best estimate, is like 1,000 times better in terms of memory safety vulnerabilities, because they're still unsafe, so it's not 0. So 1000x with that decay rate means that like a line of C++ takes about, I don't know, 15 years or something to be as safe as a line of Rust, approximately, maybe more. Yeah, production systems are risk averse. So like, yeah, we got to do the gradual migration thing. You can't like defeat a bunch of existing mitigations for the first time you introduce the line of Rust. So you have to always be improving things. You also have to always like know what went wrong if there is a vulnerability. So that's an important constraint. Yeah, so we've got this all these vulnerabilities. This is this mythos thing. People are freaking out. Like like some people are freaking out. It's definitely creating a lot more intention on, I think, a very much pre-existing problem in our industry, right? So we've got like, yeah, we had the old code is safer rule, but maybe now old code isn't much safer. There's going to be a lot of focus on like, can we have provably correct software, especially when it comes to vulnerabilities like that. So yeah, it's going to create a lot of pressure. I think these like open source libraries that everyone uses kind of at the leaves of their build tree are going to be the way in. There's a lot of toolchain integration that has to happen, build system stuff that like these many companies have to do. But once you're in, like you can kind of snowball from there. So yeah, that being said, we can't just like start from the leaves. This is supposed to be a build graph. It's kind of hard to read. You can't just start from the leaves and like slowly work our way up. The coordination just like takes too damn long, honestly. If your build tree is like 10 levels deep and it takes like 3 to 6 months to get everything in line, like you're waiting like 10 years, right? So, or 6 years. So you need bidirectional interop so that you can do your migration in like a decoupled way. Yeah, don't make everyone involved be an expert in both languages. So like minimize the maintenance overhead for maintainers of an existing library. That's a really important constraint that you see. An example of this is like, so with overloading, like it should not be a breaking change at an overloaded method, like it isn't today in C++, and therefore it shouldn't be if you have Rust callers, because then like you're taking away tools that people have to like develop their APIs, right? Taylor Kramer and I gave a talk about many of these details at RustConf last year, so if you're interested, go look at that talk. So I've got like a minute left. I don't know how long, but yeah, minute. Great. All right. So yeah. So how do we actually set Rust up for success here? I don't know the last time we've done like there's a lot of work to be done on like build system and creating like a polished experience across toolchains, compilers, language, and libraries. I can't remember the last time we had like a really coordinated effort. For those of you going to the all hands, I'm co-hosting a session with Nico about like North Stars and how can we do this kind of cross-cutting effort. Maybe have like a cross-cutting team to aid it with that kind of coordination. So I invite you to join us for that. Yeah, I just want to end very quickly on with a note of gratitude. I'm very grateful that I get to stand up here and talk seriously. mostly about the future of Rust and its success, and that I get to work with all of you. I know the Rust project has its problems, but my life has been like much better for meeting and working with you all. So thank you.
Okay, we did lie slightly to Tyler. We have time for 1 or 2 questions. So, all right, let's get what we can in.
Do you think that it's maybe important to prioritize stabilizing Rust's ABI and maybe making dynamically linked libraries available as part of this Interop effort?
Yeah, great question. I do think ABI is important. It's not well, it's not important for the kind of code that like you know my my employer works on. Just because we're able, like Google is able to like just recompile the world. So it's not something I'm particularly focused on right now. But yeah, I do think in like the fullness of time, like we should definitely. Not even the fullness. No, yeah, I think it's important. I love to see like Krabby, that kind of thing. That's definitely part of the lingua franca vision. So yeah.
Yeah, thank you for the great talk.
Thanks.
Are there either categories of or actually specific examples of trade-offs that this makes harder? Like, are there things where we should be careful about doing things that are, you know, oh, we all want this because that'll actually make it, you know, more difficult to do interop?
Sorry, is your question? Are there? Sorry, is your question that whether like doing interop makes other things harder, or could you say one more time?
Yeah, sure. I suppose for a bit more context, my you know, all interesting problems have trade-offs, right? Design trade-offs.
Mm-hmm.
We're very used to that in the Rust ecosystem. What I'm wondering is the idea of having good interop in tension with other like broad you know, themes that we want for the language, and not to imply by that question that means we shouldn't do interop, but rather are there places where we should really be thinking deeply in the standard Rust, like, oh, maybe we can, you know, come up with a brilliant solution that lets us avoid the trade-off. Where should we be putting our, like, you know, really hardcore thinking effort into breaking trade-offs?
Yeah, yeah, that's a good question. I mean, it certainly is opportunity cost, right? Yeah, I mean, I think the main trade-off is like, yeah, we're gonna have to surface primitives that let you do weird stuff, right? I mean, yeah, TR was talking about overloading earlier. Like, we're gonna surface some primitives that let you basically, you know, we'll call into C++ overloaded APIs, but then that means you can simulate your own Rust overloaded API, and some people don't like that. There'll be friction to it, like. So it's like we have tools at our disposal to like make it sort of go down smooth. But these are also primitives that like are used within the core language itself, at least in that case. So we're kind of more just like stabilizing the stuff that like gets used in the core library. So that's an example of like where I think we found a good way to balance that trade-off really well. You know, maybe there will be things that we run into where it's not that clean. You know, I think template instantiation is another like really hairy one that we didn't really dive into, and that might require some like compiler APIs, maybe some hackery. So like that one is a more open question for me. But those are like the two biggest like obstacles that I'm currently aware of. The other there's like a long tail of like weird stuff that's just gonna like. We need to make Rust more expressive to be able to express like weird memory layout, like types with weird memory layouts and so on. So like, yeah, we're gonna make Rust more expressive, and like that's gonna add more different kinds of traits and things that you might have to think about. But like, we also want those for GPUs, and we also want those for like other like environments. So I think that's the core thing. But if we're making Rust like a better version of kind of what it is already, I think we're gonna want to go down that path anyway. So, yeah.
Thank you again, Tyler, and thank you for answering those questions.
Yeah, thank you.
That is the end of the Rust project track for the day. Thank you for being here. The closing will be starting in 3 or 4 minutes in Cinema 12, which was where the main track was. If you were a speaker, please in particular get over there in time because I believe they want you for some sort of, photo thing. Thank you, everyone.